Okay, the point of this section is to relate these two concepts, invertible matrix and non-singular matrix. And the conclusion that we're going to arrive at is that a matrix is invertible if and only if it's non-singular. These are just two different ways of characterizing the same type of matrix. Now remember what invertible means. Invertible means that if you have the matrix A, there exists another matrix A inverse such that A inverse is equal to A inverse A is equal to the identity matrix. And remember also what non-singular means. Non-singular means that the equation AX is equal to 0 has only the trivial solution. X equals 0. All right? So we're going to say that if a matrix has an inverse, then it has only the trivial solution. And if the matrix has only the trivial solution for this linear system, then the matrix A has an inverse. This is actually quite similar to the situation in real or complex numbers. For instance, if you have a real number A, when does A have a multiplicative inverse? Well, 1 over A exists if A is not equal to 0. Okay, so A has an inverse if it's not equal to 0. So that's kind of analogous here, that the matrix A has an inverse if and only if the equation AX equals 0 has only the trivial solution. Okay, so it's kind of a related concept. Now here we get to the first step in the theorem. We're going to get to this final result by means of several theorems. So let's read this and get some idea of the proof. Suppose that A and B are square matrices of size n. Okay, n by n matrices. They're both the same size. The product AB is non-singular if and only if A and B are both non-singular. So in other words, if you got two non-singular matrices, multiply them together, you will get a non-singular matrix. On the other hand, if you have a matrix that's the product of two non-singular matrices, then both of them are non-singular. So what is this theorem like? This theorem is like if xy is not equal to 0, if and only if x is not equal to 0 and y is not equal to 0. Right, that's certainly true. So this is kind of a matrix version of that theorem that we know from basic arithmetic. Okay, now, since this is a if and only if proof, the proof has two parts. First, we have to go the forward way, and then we'll go the backward way. Forward way means that we're assuming AB is non-singular, and we will prove that both A and B are non-singular. So in the forward proof, we're assuming this statement, AB is non-singular, and we're proving as a result that both A and B are non-singular. Okay, so let's assume that AB is non-singular. Now the steps we're going to take is, the first step is we're going to show is that B is non-singular. And then the second step we're going to show is that A is non-singular. Okay, so we have our non-singular product, and I want first of all to show that B is non-singular. Okay. All right. This first proof will be by contradiction. Suppose B was singular. Okay. Then there is non-zero vector Z that's a solution to the linear system with matrix B and vector 0. If there is such a solution, then we can take AB times this vector. Now, because of the associativity, we can rearrange the parentheses. Since B is singular, we can say BZ is 0, and that means AB times Z is 0. But Z is a non-zero vector. What do I conclude from this? I have AB times a non-zero vector equals 0. That means that AB is singular. This is a contradiction. Remember, I'm assuming that AB is non-singular. So the fact is that you can't possibly have B as singular because that contradicts what I'm assuming about AB. All right. So B is non-singular. Okay. Now we're going to prove part 2. Part 2 we're also going to prove by contradiction. Okay. And how do you prove by contradiction? You suppose the opposite, and then you derive a contradiction. Okay. So let's suppose that A is singular. Of course, this is the opposite of what we want to prove, and we'll show that this, in fact, is impossible. All right. If A is singular, then we can find a solution Y. That's a solution to the linear system A0. Now remember, that means that we can find Y such that AY equals 0. There's some Y that exists that makes AY to be 0. Okay, now consider the linear system with vector B constant Y. What does this linear system actually look like? Well, LS of BY is the system. I can write it this way. I could write it as B times some vector, we'll call it W, equals Y. B times W equals Y. Okay. Now, we already proved from part 1 that B is non-singular. B is non-singular. So we can use that fact to conclude that there is a solution. There is, in fact, a vector W that satisfies BW equals Y. Okay. Now, it's a unique solution. It's not the 0 vector because you can't have B times 0 be equal to a non-zero vector. Okay. So, what do we have? Let's take this step by step. We've started with a solution Y to AY equals 0. We've used the Y to construct a W such that BW equals Y. Let's now apply the matrix AB to the vector W. Well, we're going to do something similar to what we did in part 1. We'll take A applied to BW, but BW is equal to Y. That's how we defined W. Okay? Now, so we have AY, but AY is equal to 0. So what have we found? We've showed that ABW equals 0. That means that W is a solution for this linear system. From that, we can conclude that AB is singular. W is a non-zero solution. That's important. Right, because ABW equals 0 has a non-trivial solution. That means that AB is singular. But we assumed at the very start that AB was non-singular. It's a contradiction, so A is non-singular. Okay? Now, I mentioned way back here that when you prove if and only ifs proofs, you have to prove both ways. We have just proven that when AB is non-singular, then A and B both must be non-singular. We have to go the other way as well. So the second half of the proof is assuming that A and B are both non-singular. And the conclusion we'll want to draw is that AB is non-singular. Right? We're also going to prove by contradiction. Right? What does contradiction mean? It means I assume what I suppose the opposite of what I want to prove and show that I get a contradiction. Okay? So I'm going to suppose that AB is singular, which means that the linear system with matrix A, B, and vector 0 has a non-trivial solution, and I'll call that solution X. Okay. In that case, I'll have 0 equals AB times X, which is equal to A times BX. Now, we have that A is non-singular. Okay. Since A is non-singular, the only way for this to happen is that BX must be 0. Okay? Because we know that A is non-singular. But B is also non-singular. The only way for this to happen is when X is 0. Okay? Now, this is a contradiction to the supposition that AB is non-singular. We started out with X non-zero, and we ended up with X having to be 0. So this is a contradiction. So we can conclude that our supposition that ABX equals 0 has a non-trivial solution is incorrect. That means that AB is non-singular. All right, so even if you didn't follow all the ins and outs of that proof, the final result is that the analogy of this arithmetic statement, if you have the product of two numbers are not 0, then both numbers are not 0, and vice versa. With matrices, if you have the product of two matrices is non-singular, then both matrices are non-singular, and vice versa. Okay, so just remember that. All right, take note of this paragraph as well. It says the contrapositive can also be used. But the contrapositive says if you have two matrices and their product is non-singular, then one or the other, or both, must be singular. On the other hand, if A and B, if one of A and B is singular, then the product is singular. Okay. All right, let's go on to result number 2. It says one-sided inverse is sufficient. Suppose I have two square matrices of the same size such that their product is the identity. Then the product in the reverse order is also the identity. Pretty amazing that you can switch these around. Now remember, matrix multiplication is not commutative, so it's quite amazing that in this case you can actually switch the two matrices. Okay, so how do we prove this? Okay. We're going to use the theorem that we just proved. First of all, consider this assumption. AB equals IN. What does the theorem that we just proved tell us? Well, IN is non-singular. That means A and B are both non-singular. If they're both non-singular, in particular, B is non-singular. Now, by this previous theorem, we know that there is a matrix C such that BC equals the identity. Okay? So, let's follow this through. Now, at this point, it's just algebra. Let's figure out what BA has to be. Well, I can clearly multiply BA on the right by IN. That's not going to change anything. By this theorem CINM, I know that I can write the identity as BC. Now we use associativity to rearrange the multiplication. We collapse this into the identity, and we get BC, which again collapses into the identity. So we've finally shown that the matrix BA is also equal to the identity. So another way of saying this is that any right inverse for a matrix is also a left inverse. If you multiply on the right, get the identity. You also get the identity when you multiply on the left. Finally, we get to the theorem that we're interested in. Remember at the beginning of this video I said we want to prove that A is non-singular if and only if it's invertible. Okay, so we want to show if it's non-singular, then it's invertible. And we want to show that if it's invertible, then it's non-singular. And we've proven enough, so actually both ways are quite simple. First of all, let's go the second way. Assume that A is invertible. If A is invertible, I can write the identity as AA inverse. Now the identity is non-singular. That means that both of these must be non-singular. In particular, A is non-singular. So I started with A is invertible, and I ended up with A is non-singular. So that proves the reverse direction. Now let's go the other way. Suppose A is non-singular. Then by this same theorem we used in the above proof, there exists some matrix B such that AB is the identity. Okay. So the theorem, we know that if you have a right inverse, you also have a left inverse. So that means that B must be A's inverse and A is invertible. Okay. So here we can add this condition to our list of equivalent conditions. A matrix A is non-singular if and only if it reduces to the identity matrix, if and only if the null space of A contains only the zero vector. That means that AX equals 0 has only the trivial solution. If and only if the linear system AX equals B has a unique solution for every possible B. If and only if the columns of A are linearly independent. If and only if A is invertible. Okay. Now it's interesting that we can now use this inverse to actually find the solution to the linear system, AX equals B. And in fact, we can write X is equal to A inverse B. Now that kind of looks like an algebraic equation here. If we applied A inverse to both sides, that's what you'd get. X equals A inverse B. Let's see that that actually works. If I take A times A inverse B, well, then I get AA inverse times B, which is the identity times B, which is B. So in fact, A inverse B must be the unique solution to AX equals B.